All right, guys, so in this lesson, we are going to sort of explicitly discuss the difference between ideal versus real gases. Coincidentally, we just spoke about ideal and real gases a little bit in class today, or the day that I'm recording this video, but that was basically a week ago in your time. And we will have to talk about attraction between particles and size of particles again. So this is going to be based on the kinetic molecular theory as well. There is a homework associated with this lesson, but it's just a reading. So if we have time to do it in class tomorrow, then that's what we'll do. So just write this down at the top of your second page of notes for classwork, and follow it with this aim. What's the difference between real and ideal gases? And also make sure that you add that aim to your graphic organizer for essential questions. Remember, our essential question this unit is how can we describe matter in terms of stability and change? All right, so I want you to copy down these do now questions. They're fill in the blank, but don't fill them in until we get to class. All right, ideal versus real gases. As much as we love the combined gas law, so this is the equation for combined gas law we have a lot of experience with, and it does not accurately predict the behavior of gases in all situations, which just means that there is a difference between an ideal gas, which would follow this mathematical equation, and a real gas, which is going to have other factors that influence it. So basically a week ago, I told you that we would pretend that the kinetic molecular theory perfectly described gas particle behavior, but I'm going to ask you now whether you think this is true, mostly untrue, or untrue. So while it's not actually true that the KMT perfectly describes all gases, it is mostly true, meaning it, for the most part, does describe ideal gases and real gases. But what we're going to learn in this lesson is what exactly is the difference between an ideal gas and a real gas. And at the end of the lesson, I'm going to teach you how you could encourage a real gas to act more like an ideal gas. So the first reason that we can discuss about the difference between real gases and ideal gases has to do with attraction between gas particles. Now, in most cases, the attractive forces between gas particles is negligible, and negligible just means that you can ignore the attraction between the particles because it's so small. And the property that gas molecules have that determines whether or not they would be attracted to their neighbors is called polarity. And two gases that you think might behave ideally, for instance, helium is a great example of a gas that could behave ideally. And another good example could be hydrogen gas. Now I am going to write H2 because it's a diatomic molecule. Both of them are gases. And the reason why these two might behave ideally is that they are nonpolar and they're very small. That'll come up a little bit more on a further slide. But for this slide, they're nonpolar, which means that they have no attraction for their neighbors, or at least very little attraction for their neighbors. But real gases are not all as small as helium and hydrogen. Many real gases, in fact, are quite large. And in addition to being large, some real gases actually are polar. And as a result of both of these realities, one being that they're large, then some of these molecules could experience dispersion forces. Dispersion forces are forces of attraction that exist between large nonpolar molecules. But if it's also polar, then that's even worse, because polar molecules, as you know, could experience dipole-dipole attractions. All right, so here's an example of a gas that's definitely a real gas. You probably know all about water vapor. It forms clouds, for instance, or we might think of it just as humidity. Water vapor stays gaseous until its particles cool down. But once the particles cool down and their motion starts to decrease, the particles will actually come together and form a liquid. This shows that water vapor is a real gas because it's showing that the molecules of water vapor actually do have attraction for each other. So we also have to consider the size of gas particles when we're thinking about real versus ideal gases. And it's definitely true that all gases occupy very small volumes, the particles themselves. And under normal conditions, you can ignore their size. It's negligible. So that means that gases like hydrogen and helium, which have very small sizes and very small radii, would behave the most ideally since they're so small. Now, real gases are not infinitely small. Instead, you can notice that they have some size to them, the particles themselves, and the way you could notice that is by compressing them. So if you were going to compress an ideal gas, you would be able to compress it all the way to a volume of 0. And that would be because in an ideal gas, the particles are so small that they really have no size at all. So you could just compress all of it all the way down to nothing. But for a real gas, obviously, molecules do take up some space. So when you try to compress it beyond a certain point, you'll have a lot of difficulty getting it to compress all the way. Okay, so not all is lost. Even though gases are real and don't follow the kinetic molecular theory perfectly, you can encourage even a real gas to act as if it were ideal. So just for the record, an ideal gas is one that behaves almost as the kinetic molecular theory predicts. And no gas is truly ideal, but you do need to know that hydrogen and helium are the closest thing we have. This is because the gases in hydrogen and helium are small and nonpolar. So when we want to encourage a gas that is not small or not nonpolar, vis-a-vis polar, if we want to encourage one of those gases to act as if it were ideal, there are two things we can do. And they are, you could put the gas under very low pressure. When you put it under very low pressure, you'll be allowing the particles to spread out, and that's one of the things that an ideal gas would do. And when you put a gas under high temperature, you're giving all of the particles a lot of extra velocity. And giving them that extra velocity allows them to ignore the attractions that they have for one another. You could think about two magnets that are rolling past one another. If they're rolling very slowly, perhaps they would attract each other, but the faster they roll, the less they'll notice each other's attraction. So if you wanted to do the opposite, let's say that you had an ideal gas and you wanted it to behave as if it were real, then you would just do the opposite. You would put the gas under high pressure, therefore encouraging the particles to come closer together, and you would put it under very low temperature, which would maximize the attractions between particles. And here we are at the pair-up. Just copy down these questions, including the answer choices, and we will answer them in class next time I see you. And of course, grab these summary questions as well. So at this point, you should have some notes in Cornell Notes style, and you should also have an aim and a do now and a pair up and a summary on your classwork page. Thanks for watching, guys.